Okay, today we are going to go through the example of FIR filter design. Firstly, before this, we are going to brief through the important equation of the FIR filter design, which is impulse response and also window function and also filter length. After go through the equation, we are going to the example. Example 1. Design a 20-order FIR low-pass filter based on windowing technique, where cutoff frequency of the filter is omega c 0.5 pipe radians. Design the filter based on rectangular, Hamming, and Bradman window. So, after read through the question, we go to step 1. Step 1, determine filter characteristic. So, for the question, we can know this is a 20-order FIR low-pass filter, where n, our filter order n equal to 20. And also, we have a cut-off frequency at omega c equal to 0.5 pipe radians. So our cut-off frequency equal to omega c 0.5 pipe radians. This is for step 1. Next, we're going to step 2. Obtain the impulse response. The impulse response equation is h n equal to omega c over pi sin c omega c n. We substitute the omega c we get just now, so the equation will become 0.5 sin 0.5 pi n. Okay, after this, we're going to step 3. Multiply hn with window function. So now, the impulse response will become hn equal to hd n times window function omega wn. So next, we are going to step number 4. First, we need to calculate the filter length, which is n. n equal to n plus 1 equal to 21. The next, we need to calculate the nd, where nd equal to n minus 1 divided by 2. So we have our nd is equal to 10. So now our equation will be hn minus nd, which is hn minus 10, and the equation will become hd n minus 10 times w n minus 10. Okay, now our impulse response of casual FIR filter, the equation will be this. Sin omega n equal to sine omega n divided by omega n. So we have this equation. So for the type of window rectangular, we will substitute the Wn equal to 1, and we have this equation. So from this equation, we substitute the value of n, we will get the value of impulse response when n equal to 2, h2 equal to 0, n equal to 4, h4 equal to 0, etc., etc., and so on. So we can obtain a graph. When n equal to 10, we will get 0.5. When n equal to 9, we will get 0.318. When n equal to 8, we will get 0. So, etc., etc. So we'll get a graph like this.
Okay, so now we will continue with the Hamming window function. We use the same equation, just that we substitute the Hamming window function to this equation. Then we get this equation. So, for example, when I substitute n equal to 1 to this equation, I get 0.0346, and 2 I will get 0, and so on. Okay, so from the values we obtained just now, we can plot this graph, Hamming window graph. So after we had done all the calculation, we plot the magnitude spectrum to observe the response of different systems. So in order to have a clear illustration of the behavior of the ripple, so we plot the graph in dB form. So this is the graph that plotted by using MATLAB. So we actually can use this table to differentiate the type of the response. For example, from this table, we can observe that the transition bandwidth for rectangular will be the shortest. So from here, we can observe that this curve has the shortest transition bandwidth, and the ripple is at negative 20.9 dB. So we can conclude that this is the graph for rectangular, and the rest will be using the same technique.
So after the example 1 of FIR filter design with windowing method, so now I shall proceed with example 2, which is to design an FIR low-pass filter based on rectangular window with the characteristic below. Omega p equals to 0.2 pi and omega s equals to 0.4 pi. And the difference between example 1 and example 2 is example 1 is given n equals to the number of filter is given. However, in example 2, number of filter is not stated. So we have to find it out based on the characteristic. We have to bear in mind always, in order to solve an FIR low pass filter, we have to follow the 4 steps as stated in example 1. Okay, in step 1, we shall determine the filter characteristic of this FIR low pass filter. And first, I would like to find what is omega c. And in general, omega c is equal to omega s plus omega p over 2. And since omega s and omega p is given in the question, so we can find what is omega c. After that, the second component to be determined in this step is the number of filter. And as we know, in general formula of rectangular type window, we have to determine the number of filter using this equation. And this is generally for rectangular type window only. This one should be minus. know, filter length should be a whole number. So a greater number of length is better for a FIR filter. So I will approximate this n into 11. And next, in step 2, we have to obtain impulse response of desired filter, which is we have to get to know what is Wn and also what is Hdn. Wn is equals to 1 is because this filter is designed into a window of rectangular window. In general, rectangular window is Wn equals to 1 and Hdn Having these two most important equations, so then we shall proceed to design our low-pass filter of FIR filter in step 3 and step 4, which is our last step. The reason to delay these two functions by ND is because we have to make sure this filter design is to be causal, and ND's equation is and as we know, rectangular window is always 1 all the time. So we can replace it with 1, and our function will be simplified into this one. And our design of FIR filter is done. And the next step is to illustrate it in graphical form.
Next, we will use these equations of filter that we have obtained just now to plot the graph of magnitude versus n. So first of all, we need to transform the equations to sign form, which will be this equation. And then, by substitute the number of n, as we have known that m is equal to 10, and m is equal to 10, so we will obtain the number of n from 0 to 10. And by typing the equations and substitute the difference number of n into the equations, we will get the number of magnitude, which will be, let's take the example of n equal to 0. n equal to 0, we will get negative of 0.06. And then 1, we get negative 0.047. And then when it's come to n equal to 5, we will get error. And this time we need to take the considerations of when sync 0, it will be equal to 1. So when n equal to 5, these equations will be equal to 0.3 sync 5 minus 5, 0.3 pi. And this will be 0. So the equations will be 0.3 times 1, so which will make it become 0.3. And by using this number, you can get this type of graph. Thank you.
Okay, so now I will explain the lecture note on slide 22, which is the quiz 1. So in the quiz 1, we are required to design a low pass filter with this specification. We have a damping of 0.007, transition bandwidth 0.6 pi, m lowest or equal to 12, and omega c is 1.5708. So at first, this quiz is different from the two example before because we do not know what is the window that we want to use. So at first we need to decide which is the window that we need to use for this low pass filter. Okay, so we use damping to find the window that we need to use, which is we find the damping in dB is negative 43.09 dB. So from the table we know the window that have damping is negative 43 is Henning, the type is Henning. So we use the Henning window for this quiz. And then the equation for Henning windows is this. Okay, so now using also from the table of Henning window, we have the transition bandwidth is equal to 6.22 pi over n minus 1. So for the specific given is 0.6 pi, so we can find our n is 11.37. So we get the larger numbers is 12. So using this n, we can find our n is 11. So now we have get all the requirement that we need for our equation. So we find our ND. ND is n minus 1 over 2, so it's 5.5. So we can get our hash, and HDN is like this. And then our n, we also need to minus 1.5, so we get a new equation like this. So we combine these two equations to our hash n, so we get an equation like this. Okay, so this equation is actually for the n from 0 until 11, because our n is 11, and then the hash n is actually 0 for every other n. Okay, so using this formula, we need to find the value of each n. So you can see here, so if you substitute 0 to the position of n, you will get 0. If you substitute 1, you will get 0.004. So this is all the result that when we substitute our n into the position. So you can see actually the hash 0 is equal to hash 11, and then when n is 1 is actually equal to n when 10. So here is the graph that we plot from the equation that we get. So we can see here is the filter hash n of the filter. Thank you.